You so much. It's my great pleasure to be here. So today I'm going to just talk about rectified flow. It's a method that we have been working in the last few years, and has I think it has becoming more popular as an alternative way, as diffusion model, as a simple and more efficient way. So I'm going to just basically just cover the basis of the method and just answer questions if you have any. So if you have any questions, feel free to just ask during the talk. Okay, so here the fundamental problem is that typically if we have supervised learning, then that means we have pairs of input and output, and we often just need to match the input output data. That often leads to a very straightforward optimization problem, and then you can solve it with standard optimization. So this is like very standard stuff. But then if we have unsupervised learning, the subtlety here is that we really don't have pairs of input output, and that becomes very difficult, right? For example, in generative modeling, we are interested in finding a mapping that takes a random noise, such as Gaussian noise, and map it to a set of images, right? So in this case, the difficulty is to actually decide, giving any data point or image in this case, which particular random noise should I assign to, right? So in statistics, this is the latent variable problem. Like you can view the latent, you can view the noise as the latent variable, and we need to figure out the latent variable in certain optimal way, right? A similar problem, I think more generally, happens in domain transfer, where we have two distributions, right? Just two sets of data points. And we want to find a mapping, a reasonable mapping between them so that I can transfer one data distribution to another, right? So this is a generalization of the generative model where, one of the data distribution is a Gaussian noise, right? Both of these problems are, reducing to finding a kind of assignment between two distributions. And this idea that finding we need to find the assignment is really critical, because if we don't do it, if we do it naively, we wouldn't get anything interesting. For example, let's say, for example, during the training, we just take a random pairs of independent drawn pairs of data noise and just feed the data, you can show that simply the network is going to just feed the mean vector without capture any variation of the data, right? If we don't condition on anything, we will just get the pure empirical mean, right? So this is the difficulty, and to formulate the problem, mathematically, so we assume that we have two distributions, pi0 and pi1, which is unknown in our setting, and we have observations from them, right? And then the goal is to find the mapping T such that ideally, if we have lots of data, we hope the map T actually transports sample from pi0 to pi1. So this is finding a transport mapping between two distributions, right? So this is a kind of empirical version of distribution transport problem, because on one hand, we don't really know both distributions, pi0 and pi1. We only observe it from sample. So this is really a statistical problem. But it's an interesting statistical problem because typically in statistics, we have one single unknown distribution, but here we actually have two distributions that are unknown. And another challenge is that even if you are given two distributions, pi0 and pi1, it's actually non-trivial to find a transport mapping between two given distributions if the distribution is high dimensional and continuous. This is related to optimal transport problems. It's actually computationally difficult. So it's really a combination of these two problems, statistical challenge and computational challenge. A very interesting problem. So there has been in the literature, especially in the machine learning literature, in the generative modeling literature, people have been trying to attack this problem. There are roughly two types of methods. depending on what kind of T we want to model. So if the transport mapping T is modeled as a regular neural network, so then we just want to find the black box mapping that takes pi0 to pi1, and this will reduce to the traditional methods such as generative adversarial networks and the VAEs and normalizing flows, things like that. But recently, we have people are interested in diffusion model and flow models. In this case, T is modeled as a continuous time process. So implicit define it using either ordinary differential equation or a stochastic differential equation. So basically, we want to learn a velocity field of a differential equation, which starts from random noise, and we hope to learn the velocity field in a way that at t equal to 1, we will return the sample. So basically, we are now finding a continuous process that takes random noise and return the data distribution, right? So today I'm going to focus on flow methods, which use ordinary differential equation. People also worked on diffusion models, which is using stochastic differential equations, but the barrier between these two approaches is really very blurry. So they are essentially the same thing. If I have time, I will talk about this. Now, why do we need to work on different continuous time processes? Well, because that's actually a very interesting trade-off. So it turns out if you use a black box methods, it's actually very difficult to train. So like traditional methods like GAN, you have to solve a minimax gain, which is very unstable to train. Or if you use VAE, then you really introduce approximation errors. You have to approximate the posterior distribution using a conditional Gaussian that really impacts the performance. On the other hand, if you use continuous time process, it turns out in terms of training, it's actually much easier because you can write down a nice score matching loss function. But then in terms of inference, you have to run the differential equation to actually generate data. So the inference is more expensive because you need to solve the differential equation every time when you want to generate a sample, right? So there is a trade-off between training and inference when using these two approaches. And one of the obvious goals is how can we bridge the gap between the two extremes, right? So this is actually what we're going to discuss today. But before that, I want to clarify some concepts. And one really important fact that is relevant is that given two distributions, there are in fact infinite many possible transport mappings. So let's say I have a Gaussian distribution and convert it to another Gaussian distribution. In fact, I have infinite many ways to do it because I can rotate my distribution in arbitrary ways without influence the distribution. So among all these possible transport mappings, that's a large literature on optimal transport, which is finding the best possible coupling or transport mappings. So this is reducing optimization problem where we want to minimize a convex cost function. And you can also formulate it in this continuous dynamic view where you want to find a continuous time process to connect two distributions, right? And these two formulations are equivalent mathematically, in fact. But the problem is that finding the optimal transport mapping is quite expensive in practice. And we really don't have to really find exactly the optimal transport mapping because all we care is to find a feasible mapping that can do the work of transporting T Z0 to Z1. It doesn't matter what's the transport costs we have, because here the cost is defined to be somewhat artificial. So the cost depends on arbitrary function C, which is a convex function. So typically people use a quadratic function, but you can use arbitrary functions, right? So it's not directly related to what we want to learn in terms of generative modeling. So then the question is, if optimal transport is not the most natural notion of optimality for generative modeling, then what what notion of transport mapping should we look for? But turns out we think what's more relevant is something we call street transport. So what I mean is that if we want to learn an ordinary differential equation to transport from one distribution to another, in the end, at the inference time, we are going to need to solve this differential equation. So we need to discretize the differential equation using, for example, Euler's methods, right? And then we are going to have discretization errors, right? And the discretization error is going to depend on how curvily the trajectory of the differential equation is, right? So if the trajectory is very curvily, then we have to use a small step size. As a result, we have to simulate lots of steps, right? If on the other hand, if we have a straight trajectory, perfectly straight trajectory, then we can just go one step of Euler method and exactly get what we want, right? So then really what we want is to make sure that the trajectory of the differential equation is as straight as possible, so that we can use very small number of steps to do the transport mapping at the inference time, right? So this is a notion that is directly impacting the inference speed, and that is directly relevant to the practical application of these maps, right? So then really we're interested in finding street transport, right? And more specifically, street transport is defined as, let's say in this case, it's a differential equation that takes one distribution to another. And then also the differential equation has to be like perfectly straight. Like street transport means, every trajectory has to be perfectly straight. In this case, we can write the trajectory in this linear form, linear interpolation form. So it seems to be a very simple condition, right? But turns out, the combination of these two conditions does actually impose some very non-trivial conditions, right? So it's relatively easy to understand what it means to want the trajectory to be straight, right? Now it's more kind of tricky to understand what does it mean if I want the system to follow a differential equation, right? So it turns out the key idea here is that if we want to have a trajectory to follow a differential equation, then the trajectories cannot intersect in the middle of the time. So what it means is that you cannot have trajectories that go intersects as the figure on the right side. So that's because if you follow a differential equation, then at every time point, you're going to have a unique direction to go forward. You have a unique velocity field. But if you have an intersection like this, then you cannot, then you have two directions to go. And in fact, in this case, the differential equation doesn't have a unique solution. It's not well defined. So if you want to have a well-defined differential equation, the trajectories cannot intersect. So really, we want to find a street transport. We really want to find a set of trajectories that are simultaneously straight and also non-intersecting. So really it boils down to finding a set of non-intersecting and straight trajectories to connect two distributions, right? That is the intuition. And this actually is very much related to optimal transport, but it's very different. So roughly speaking, like optimal transports for any convex cost, it has to be street transport. So it has to follow street trajectories. But on the other hand, the street transport are not necessarily optimal. So you can find cases when you have street transports but not optimal in the optimization sense. That's because you can induce these rotation components. On the right side, that's a street transport but it's not optimal. So now the problem, now we have set up the problem as finding street transport. So then rectified flow is actually a way to do this computationally, surprisingly easy way. So the idea is actually extremely simple. now that we have two conditions, one is that the trajectory has to be straight, another is that the trajectory has to follow a differential equation. So then to satisfy these two conditions simultaneously, we just alternate between these two, alternatively enforce these two conditions. So, so roughly speaking, what's going to happen is that we will start from a set of coupling that is giving us as the data set. So like we are giving observations from pi 0 and pi 1. So this is going to be our initial coupling. And then we take these initial couplings, we connect them with straight trajectories. Now this gives us a set of trajectories that are straight, but these trajectories may intersect because we are connecting these dots arbitrarily. So what we will do is we are going to enforce, so they may intersect and may not follow a differential equation. So what we are going to do is we are going to fit this trajectory using a differential equation with a neuron differential equation. So that actually allows us to get a set of trajectories that follow differential equations, but on the intersecting point, these points is going to require to ensure that they to unentangle to ensure that they don't intersect. So as a result, you will get curved trajectories, and we're going to repeat this process. Then what we are going to do is we are going to take the endpoints of the differential equation and connect them with straight lines and fit another differential equation, and we'll repeat this process. It turns out if you repeat this process, you will converge to a straight trajectory in the end. So that's a theoretical property that ensures that if you follow this process iteratively, you will eventually get a straight transport. So this is the rough idea. But now let me just talk about the same thing, but just with more concrete notations and steps. So the goal here is that we are giving two samples, pi x0 from pi 0, x1 from pi 1, and we want to train a flow, a differential equation to transport from pi 0 to pi 1. So the first step is that we will going to take random samples from pi x0 and x1 and just connect them with these three trajectories, right? Now we get a set of trajectories, and then if we simply take the derivative of the trajectories, we will get a differential equation. But this differential equation is not well defined. It's not necessarily well defined because the derivative actually depends on the initial point and end point. So every time point, the derivative xt is going to point from the initial point to the end points, right? And it cannot be solved like a regular differential equation in a causal way because your velocity field is going to depend on the final result x1. And this happens exactly when you have trajectories that are intersecting, right? So for example, if you have trajectories that intersect in the middle of this plot in the slide, you will see that you have two possible directions to go, and you cannot decide which direction to go, right? So to solve this problem, what we are going to do is we are going to take these three trajectories and we are going to feed it with a neural network. So what it does is we're going to find a neural network velocity. V is assumed to be a neural network, but now we'll just assume we are minimizing in the set of all possible functions to predict the velocity direction of the three trajectories, given the xt, given the current position. So if we solve this problem, we will actually get a differential equation. In fact, if you assume that the optimization is solved exactly in the set of all possible velocities, then the optimal solution is going to be exactly the conditional expectation. So given any point xt, the expected velocity is going to be the conditional expectation of the slope of all the possible trajectories that are passing that point. So for example, for a point in the middle of these trajectories, you're going to find, let's say if there are two trajectories that are passing the point, you're going to just average directions, you'll get a kind of the average the direction, right? And then if you actually simulate from this differential equation, we will end up with a trajectory on the right-hand side, where we can sort of say that, in fact, the trajectory is going to basically the trajectory or differential equation will try to fit the original linear interpolation as much as possible, but then at the intersection point, the trajectory has to be biased in the way that they don't intersect. So in this case, if you are from the upper cluster, you will end up with finding us going to another point on the upper cluster without crossing the intersecting point, right? Right. Okay. So now this actually gives us a differential equation that does take one distribution and convert it to another. Unfortunately, though, these trajectories may not be perfectly straight, because if they are intersecting point, then you will introduce a curvature at the intersecting point, right? But what we could do is we can actually repeat this process. And in fact, in this case, if we repeat the process, we'll actually get a pretty straight trajectory. So what's happening is that after we train the first differential equation, we will actually reconnect the starting point and end point of the differential equation with a straight trajectory and repeat the process. We'll fit another neural network to get another ODE. And if the straight trajectory don't intersect, then we will actually fit a differential equation that is pretty straight, right? So I think here, this is a plot that kind of illustrates, kind of zoom in what's exactly happening at the intersection point, right? So let's say here at the bottom of the slides, you can sort of, if we have two trajectories that have intersecting area in the middle, right? Now, if we feed the differential equation the expected velocity, you will see the trajectory that goes along the red trajectory. So you can sort of see that in the intersecting region, the particle is going to follow the average direction of the two possible trajectories, right? And then if you go outside of the intersection area, you will follow the original trajectories, right? So, and in this way, it happens to make the trajectory rewire because you have to travel horizontally in the confusion region, so they don't intersect even in the intersection region, and as a result, you will have this rewiring effect. So once again, this is the overall algorithm. It's a very simple process, in fact. So we will start from the observed distribution x0 and x1. And then we will use that trajectory to train a differential equation to feed the curve of the linear interpolation. And then we are going to simulate pairs from the differential equation to get a new pairs of Z0 and Z1, which is the noise and the corresponding image. And then we are going to feed another differential equation again, and then we will repeat. Now, typically, we only do one step, one or two steps. And that actually already gets pretty straight trajectories, which enables us to get faster one-step generation. But theoretically, if you do lots of steps, you will in the end converge to straight trajectories. And of course, in practice, there is going to accumulate lots of errors if you do lots of steps. So in practice, we really just do one or two steps. This is actually the algorithm. I think I want to stop here to see if there are questions.
Can I ask a clarification question? And also,
yeah.
And if you want to ask a question. So yeah, I think I understand the overall high-level logic of the training objective, but I'm a bit confused on the crossing part, because I feel if in a high dimensional space, like an image, this very high dimensional space, if you randomly draw two straight lines, then most likely they won't really have crossing. So I'm curious on, I mean, on 1D or 2D, you can easily get crossing as this illustrative figure said.
Yes, that's correct. Well, there are two aspects of this. One is that let's say even if you are in high dimensional space, if your noise distribution is Gaussian,
Yeah.
like your distribution is is a continuous absolute continuous distribution, then there will indeed theoretically be intersections, right? So at giving any point, there will you can find trajectories, multiple trajectories passing at any given point because the Gaussian noise is everywhere. Right? Theoretically, there is going to be intersections, even in high dimensional space, right?
I think you're matching a Gaussian noise with an image. Is that correct?
Yeah. So let's say, well, pi 0 is Gaussian noise, and pi 1 is your noise, is your image, right? So then let's say even if you have two images, right? Then giving any point, you can find the trajectories that pass that point and end up with any of the two images. So there will be intersecting everywhere in practice, right? So that's one aspect. Another is that if your pi 0 is not Gaussian, for example, you want to do a transport between a set of image to a set of image, right? Or you want to do the reflow, which is the second step, where you start from the result from the first flow. In that case, practically you don't have intersections because as you said, if both your pi 0 and pi 1 have limited number of points, then practically you may not have intersections. So then what's happening is that if the two trajectories are really far away from each other, then that's actually a very good thing because that means that you can actually train a differential equation that don't intersect, and that means you already get a straight trajectory, and that's really good. And this is what's happening at the reflow step. If you really don't have intersections, that's great because now you really get straight trajectories, right? But that's another case where you don't have exact intersectings, but the trajectories are very much close to each other. So in that case, what's going to happen is that the neural network is going to kick in because in practice, you are feeding a neural network. A neural network is going to be smooth. So then even if you are if trajectories are not exactly intersecting, but if they are very close to each other, then when you feed the neural network, you will kind of, have some sort of soft intersecting. So neural network is going to treat them as intersecting. So that in that case, you will actually also see curved trajectories. Yeah.
Yeah, thanks a lot. Yeah.
Can I also ask a question? Just to clarify, so in the reflow step, the training data, they are not from the original training data set. So do you take Z0 K plus 1 to be from like pi 0 and then you solve for Z1 K plus 1?
Yeah, that's a very good point. So actually what's happening, you can do, okay, so after you get the first differential equation, you can do two ways. One is you can take a random noise and simulate the differential equation forward so that you can get simulated data. In that case, the data is not from the real data, but it's simulated from the first model, right? So this is one way. Another way is you can actually take a real data set. You can take a real data from pi 1 and then simulate differential equation backwards. So in that case, you will get noise. You will get simulated noise, right?
I see. So either direction is fine.
either direction is fine. And I think in small data set, we tried like both directions. We even combined them like half. We didn't find much difference in small data set, but later people report that if you do the backward, it seems to be better. So I think it'll be interesting to consider both directions and see if combining them or which one is better. Yeah.
Okay, thank you.
Are there any other questions? Okay. If not, I will keep going. So theoretical properties. Well, turns out it has a number of important properties that ensures that this method actually works. One is that is marginal invariance. So what it means is that if you take an arbitrary so you take an arbitrary coupling x0, in fact the arbitrary pair of random variable x0 and x1. So x0 and x1 doesn't have to be independent. They can be arbitrarily dependent. So then we can ensure if you solve that optimization, feed the ODE exactly, then we can ensure that the pair of Z0 and Z1. So Z0 and Z1 is the endpoint from the differential trajectory, differential or equation trajectory. So we can ensure that Z0 and Z1 follow the same marginal distribution, right? So in fact, what we can show is that we can show is that, let's say, for example, we start from x0 and x1, we connect them so we get a set of linear interpolation trajectories, right? And then we feed that linear interpolation trajectory with a differential equation. You can show that at any given time point, even though the differential equation trajectory is very different from the original one because you have to rewire the intersecting and become curved. But then at every time point, xt, they have the same marginal distribution. So if you fix the time t and check the marginal distribution of xt, which is from the linear interpolation, and the zt, which is from the differential equation that is fitted with the linear interpolation. Turns out these two distributions are exactly the same for every t. As a result, you have the same marginal distribution from 0 and 1. So this property ensures that in the end, we will get a sample that approximately follow the data distribution, right? So another nice property is that this procedure of feeding a neural network of the linear interpolation process, we call this process rectified step. It turns out this rectified step always decrease every possible convex transport cost. So it's a pretty strong property. So let's say, for example, you take your original coupling, x0 and x1, they could be from independent jaws. So you have, let's say, independent coupling of your noise and data distribution. So you can calculate its transport cost. So that is x1 minus x0 of some convex cost function. Cost can be quadratic loss or any other loss. And then you get the coupling from your differential equation after the rectification. So you get a Z0 minus Z1, and you can also calculate convex cost. It turns out for every convex cost, the coupling that you get from the differential equation is going to have less lower or equal costs, right? So this procedure actually decrease the transport cost for every possible convex cost, right? So this is another thing. So intuitively, you can sort of see that if you have, like, say, for example, quadratic cost or L1 cost, you can sort of see it from the plot where you have this, you can simply apply a triangle inequality and get the result, right? And the third property is that if you repeat this process, you will in the end get the straight flow. If we have time, I will give the exact precise statement of this result. And this is a illustration of the result, empirical result. So if you the top row is the trajectory, like is the first flow that we land, because the initial linear trajectories have intersections. So then you can sort of see that the first trajectory is not perfectly straight. The way to say it is that here the n represents the different discretization step. If the curve if the trajectory is curved, you can sort of see that the different discretization steps will give you different result. And you can see that when n is very, very small, you get blurry images, because in this case, the discretization have large error. If you reflow and do it another time, you will get much straight trajectory. You can see from here that no matter what discretization step you have, you will get pretty consistent images, right? And the same phenomenon holds if you have transport from one distribution to another. In this case, a human face to a cat face, you will get a similar effect. So this idea has been it turns out this idea can be naturally extended to conditional generation, where instead of transporting one distribution to another, you will also condition on a prompt, right? So in that case, everything is conditional on prompt, and you will take, let's say, for example, you want to take a text prompt and generate image. In that case, you really want to solve you want to estimate conditional distribution, right? So the same thing holds if you just adding a condition on the neural network, and every time you will collect the pairs of prompt and the noise and data and do the linear interpolation as before, and the same procedure holds. It turns out this simple procedure has been really useful for generative models, and people has been studying using this method, and for image generation, video generation, lots of other domains. So that's exciting that this method really scales to very large models. Any questions?